Assalamu alaikum. Can you hear me?
Walaikum salam. Yes.
Good. Can see the best number of students today. But it is already. Yes, this is the last makeup class. Inshallah. You will get some video lecture on labs, but you don't need to attend those video lectures. You just need to go through them. Yes, no more. No more. Okay. So let's start our class assignment number 7. Um, first, my screen. Can you see my screen?
No, we can't. Yes, now we can.
Can you recognize that the video is going on? The recording is going on.
Yes. Let's record.
Okay. If yeah. So if any time if you find that that sign is not there, recording is not happening, just let me know. Okay.
Okay.
Okay. So let's start with our first problem, question number 1. This is a number, it's a floating point number. Can you see all of them? All of you, can you see?
Yes.
Yes, Doctor.
Okay. So this is the first problem that this is a fractional number. You can see this is not an integer number. You can see this is a fractional number, 75.8325. Now this fractional number we need to represent using IEEE 754 single precision floating point number as a single precision floating point number. As you know that single precision floating point number as per IEEE 754, we need total 32 bits. For single precision, we usually use 32 bits. For double precision, as per IEEE 754, we use 64 bits. Since this number, the fractional number that we have got here, need to be represented using single precision, that means using 32 bits. So we'll use 32 bits for representing this number. Now, out of these 32 bits, as we know, that 1 bit will be used for the sign, 8 bit will be used for the exponent, and remaining 23 bits. Yes, 23 bits will be used for the mantissa or fraction. So first thing first, we need to convert this non-fractional number, that is 75, to binary, and this fractional part also in binary, but their representation or their conversion method is not same. So first 75 should be represented. If you see, 75 can be represented as 1 plus 2 plus 4, then 8, 16, 32, 64. So we'll take 64, then we'll take 8. So 64 plus 8 is 72, plus 3 equal to 75. Are you understanding? Are you following, everyone? So this is a representation for the 75, which is the non-fractional part of this number. So we have just converted with their positional value. You can also do it by dividing it by 2, and the remainder dividing by 2, by the remainder dividing by 2 remainder. That is another method of converting any decimal number to a binary number, but we can use the positional value. This is a positional value 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64. So we are taking 64, and then this one is 8, that's 72, then plus 3, 75. Any question, any confusion?
Clear.
Okay, now we have a second part, which is 8325. This is a fractional part. As we know that any fractional part, if you want to convert it to binary, you just have to multiply by 2. And when you multiply by 2, the result that you will get before the decimal point, that will be your binary bit. the, after the decimal point, the number will continue. So if you see that how we can do that, let's start 8325. You can see that 8325 we multiplied by 2, then we got 1.665. Then we'll take 1 as our binary point. Then 665 will be again multiplied by 2, 1.33. This one is our binary point. Then 33 will be multiplied 0.66. So 0 is our binary digit. Then 0.66 multiplied by 2, 1.321 is our binary digit. So we can keep continue it like this. The more you go, more better precision you will get. Try to understand. The more you will go until you get all zeros, you can see that we can go after that as well. So the more you go, you'll get better precision, and that's the reason actually our mentees, our fractional part, if you can spend more number of bits, you can get better precision. Okay, so here we have gone up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I have gone up to 17 bit. You can go up to 23 bits because or 24 bits, because we have that number of bits for our Mentisa. So I have just gone up to 17 bits, but you can continue with that one. But if you go with this one, it will give you the precision up to at least 4 or 5 digits. So that will be fine. Okay, so this is our number 11010101000111101. That's our fractional part. This is our non-fractional part. So total number, we can say the total number 75.83, 75.8 point 8325 equal to 0.100. So we can remove that 0 point. Then this is 1101. So 1101. Then 0101, then 000. Then this is 0, then this 0, then this 0. So 000. Then 4 ones, 1111. Then again 01. So that's our total representation of the fractional value 75.8325. Are you following?
Yes. But Doctor,
Any question?
yes.
Yes.
When I can stop, like 16 is the safe side, or like
15 or 16 is the safe side? No, in this particular case, you can see still there is a fractional value. When you get 00, then that is the safe side. That means that is completely represented. But if you don't get 00, you can go up to 23 times. But in the exam, I am not telling you to go up to 23 times. Are you understanding? In the
yes,
exam, if you go up to 8 to 10 times, that will be fine.
10 to 8. Okay.
Okay, provided that your number is like that, where you have a still some non-fractional values. Are you understanding? You can
Yes.
continue. In that case, 8 to 10 times will be fine. Okay,
Okay.
at least. So this is our total number 75.8325. This is our the binary representation of the number. Now you can write it in scientific notation. In order to write it in scientific notation, definitely our binary point should be shifted here to the left. So if we shift 1, 2, 3, 4, 5, 6, we are going to shift 6 bit to the left. And since we are shifting 6 bit to the left, so it will be into to the power, it will be to the power plus 6 or minus 6. Are you there?
To the
Anyone is
right
there?
or the
Is it a plus 6 or minus 6?
-6?
If you shift to the left, it will be plus 6 or minus 6.
Plus.
Uh-huh. I can see only 17 students. Okay, so is it going to be plus 6 or minus 6? Tell me. You are shifting to the right, is not it? Sorry, shifting to the left. this binary point is going to be shifted here to the left. So it will be plus 6. If
shouldn't be plus 6.
Yes, it should be plus 6. So what will happen? 1.001011. This is this one, and then your normal fraction 110101000101010101, then 000, then 11101. So to the power, so we can write the full and into to the power plus 6. So remember one thing, when you are shifting to the left, the exponent will be plus. When you are shifting to the right, exponent will be minus. If you have a still problem with the scientific notation, then it's a really problem. Now,
Doctor?
Yes?
I think there's a mistake in the previous one where we found the decimal place.
Which one?
If you look at the 7th line from the left side where we have 0.64 multiplied by 2, we got 1.28, then you put 1.28 in the answer as well to the left side.
Yeah, that's not a mistake actually. That's a
You just had a typo of 1.
yeah, that's the type. Yeah, but the result is still same. Not
Yes, it is. The answer is correct.
okay. Answer is correct. Okay. Now we are going to the biased exponent because our exponent is plus 6. Exponent is plus 6. What will be our biased exponent? Can you remember that? What will be our biased exponent? Is there anyone? What will
I
be
don't exactly remember that one, unfortunately.
you missed the class. What about the other students? So really unfortunate. 40 students did not get anything. What is going on? Is there any other student? Okay, so the biased exponent will be the plus 6, which is your exponent. You need to convert your original exponent to the biased exponent. In order to convert your original exponent to the biased exponent, in case of single precision, you have to add 127 to it. So we have to add 127 to plus 6. So 6 will be added with 127. So this is our biased exponent. So when we are going to store it in our computer memory, we'll store the biased exponent. We are not going to store the original exponent. Remember one thing, we are going to store the biased exponent. We are not going to store the original exponent. So 133 will be stored in the exponent part. As you know that 1 bit for the sign, 8 bit for the exponent, and remaining 23 bits for the mantis or fraction. So this our 8 bit will be used to represent value 133. So now let's represent the number, this 75.8325. First, we have to convert it to binary. Then you have to write it in scientific notation. Then you have to find which one is our exponent, and this one is our mantissa. And now exponent need to be converted to the bias exponent. In order to convert it to bias exponent, we have to divide it. We have to add 127 to it. So we have got 133. Now, once we got 133, now we can get all our parts of, that we are going to represent in computer memory. Our sign is 0 because this is a positive number. Sign is 0. Our exponent is 133, which is our biased exponent, and 133 can be represented just a normal binary value. So you can check, this is your the position value is 1, this is position value 2, this is 4, this is 16, this is 32, this is 64, this is 100, sorry, 1, 2, 4, 8, 16, 32, 64, 128. So this is 128 plus 5 is 133. So we have taken 133. This is just a binary representation of 133. There is no sign bit. You don't need to be worried about sign. Just a binary representation of 133. That's why we convert our exponent to the bias exponent, and in order to convert your original exponent to the bias exponent, you have to add 127 to it. Now this is your exponent 1000101, that is going to be stored in your exponent part, and your fraction is basically this part is your fraction, because we are not going to store one dot. We don't need to store that one, because it is always the same one dot. So we don't store one dot as in your fractional part or in the mantissa part. We just going to store this one. So if you see the total representation, your sign bit is 0 here, your exponent is 100000101, that's your exponent, and then remaining is your mantissa, and you can see that 001011 001011, then again 1101 1101, then 01010000, then 11101. So I think we have got 23 bit here. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23. So we have exactly used 23 bits for representing our whole mantis and fraction. So you can see that is a real representation, actual representation of your 75.8325 in computer memory. That is the way how using 4 byte the number 75.8325 will be stored in computer memory. Is it clear to everyone? Can I go to the next problem?
Yes.
Okay, it looks like that we have only one or two students. The other students are busy with some tea, coffee, or kawa. So let's solve the problem. The question number B. First, what we need to do, minus 123.8125669. And in this case, try to understand, we have to use double precision. It's not going to be stored using single precision. And you can understand, in case of double precision, you have 1 bit for the sign, 11 bit for the exponent, and remaining 52 bits for the mantissa or fraction. So 52 bits for mantissa and fraction. Since you are getting higher number of bits or more bits for storing the fraction or mantissa, that's why you will get better precision. So as we usually we know the double precision, you can get after the decimal point, you can get precision up to 12 bits, up to 12 digits. Up to 12 digits you can get the precision. Anyway, so we are going to use 64 bits for representing this number. So first thing first, 123 we can represent in binary. So in order to represent 123, we are not worried about the sign, just 123. We are representing it binary. Now you can see this 1 is the first positional value, then 2, then 4, then 8, then 16, 32, 64. So we are going to take 64 plus 32 is 96, plus 16 is 112, plus 8 is 120, and plus 3 is 123. So this is our representation of 123 in binary. Once we got the representation for 123, now we can represent 81256669, and this one we are going to represent convert it to binary. You can see that 0.81256669 multiplied by 2, 1.6251338. Again, I think I'm just showing the result. I'm not just multiplying it by 2. I'm not showing the result. I'm just showing the result. What will be the result? Are you understanding this one? So basically what you have to do here, you have to write 0.625138 multiplied by 2 equal to this one. So 0.625138 51338 will be again multiplied by 2, so we'll get 1.25026276. Then this one will be again multiplied by 2. This one will be again multiplied by 2. this one will be multiplied by 2, and then finally we'll get 0.500 this one. Any question, anyone? So I'm not showing the whole thing, I'm just showing the result. What will be your bits, binary bits. So your binary bits will be 1101, then 000000000, then again 1000100111, and it will continue up to so many bits. Actually, how many times I have actually multiplied it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45 times. Actually, you don't need to go 45 times. Definitely in the exam, you can go until 9 or 10 times. Yes, any question?
Doctor, actually, I have two questions. When in all the multiplications we put 0, 0 dot 0 point and the number, even if the result was 1.
Yeah, I did not understand your question. Can you ask the question in a different way?
Like the first line here, it's 0.8125, and the result was
8125669.
yes. Okay, we
The
multiplied by
result
2.
is 1.6.
Yes.
And result is 1.6251338. That's your one. That's your first bit of the binary.
Okay.
Then you have to work with the fraction. You have to work with the fraction 6251338 multiplied by 2. Then you will get 1.2502626.
Instead of putting 1.625 in the second line, I put 0.625.
Yeah, you have to work with the fraction only. Where are you?
Okay. You said before we can stop after 10 times or 10 times of this fraction
Yes.
multiplied. Can we do it now? Because
Yes.
it's too much lines and there is no space.
Yeah, so I'm just showing you. So not necessarily you have to do it in your class assignment. If you don't have the space in the class assignment, don't do that. But I think there is enough space in the class assignment because there's a whole page. You can make 2 rows. You can write. If you can write, you can write. If you don't write, you don't write. Who is going to
we can
force you?
write like actually maybe 10
Yeah, 10 times. Yeah, no problem. If you want to write 10 times, write 10 times. But you have to understand which one is your binary digit. So this is your 1 is the first binary digit. This is second one. This is third one. This is fourth one. Then this one is 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th. So up to 13, you will get all 0, 0, 0, 0, 0. So if you actually stay up to 1, up to 4, and after that actually this up to 13 you are not getting anything, you are getting all zeros, then you will get one extra one. Because of getting that one, you should go up to 14. Either you go up to 14 or you stay up to this one. That's it. Leave it after that. Are you understand? If you go up to 14, you will get maybe very close to 812 maximum. You get the precision like this. But if you get more precision with this one, then you need to go more. Anyway, so that is the how to convert a fractional part. I don't want to spend a lot of time with that one because you have already learned that one in your binary fraction. Yes. Any question, anyone?
Doctor,
How would the representation of the 14-bit only look like if we're not going to take the full 45 bits there?
Sorry. Yeah, what we'll do, we'll take the fraction first 5 bits, 8 bits, 10 bits, 12 bits, 14 bits, and then remaining will be all zeros. Are you understanding?
Okay, thank you.
Okay, remaining will be all zeros. So we'll see that one here. So what we are going to do, we are going to write in scientific notation now. If you write in scientific notation, first of all, your this is your 123. So we can write that one 123. So this number is 123.815. What was the number? 8125669. 8125669 equal to this. So that's the representation of 123. Then decimal point. Then we have 1101. So we can write 1101. Then we have 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Then 1000. So 1000. If we stay, you can leave it like this one. And if you see this one again, fortunately or unfortunately, again your decimal point need to be shifted to the left. As we know that when you are shifting to the left, the exponent will be plus. When you are shifting to the right, exponent will be minus. So since you are shifting your decimal point to the left 6 digit, fortunately it is also 6 digit in this case as well. So what will happen? This will be 1 point, then this is 111011, then again 1101, then all zeros, then 100. So that's your fraction. So into to the power 6. So we have not used total 45 bits. We have just used this number of bits. I think 13 plus 4, 17 bits as well. Yeah. Then what is our biased exponent? The biased exponent is what you have to do for double precision. When your original exponent, you want to convert it to biased exponent. In case of double precision, you cannot add with 127, rather you have to add 1023. So your biased exponent will be now 1023. So what will happen? 6 will be added with 1023. So your biased exponent is 1029. Now represent the final number. Let's represent the final number using 64 bit. Using 64 bit.
Doctor,
Sorry.
what's about the sign here? We don't the sign we didn't.
Okay. Sign. Yeah. We can keep this sign. So represent the number using 64 bits now. Okay, so let's see what we are going to do. So this is our sign bit. Actually, this is our sign bit because our number is negative. So sign bit is 1. And what about 1029? This is a representation of 1029. This is using 11 bit. As you know that in case of double precision, you have to use 11 bit. You have to use 11 bit for representing your biased exponent, and you can see that your biased exponent is 1029, and this is exactly 1029 because this is 1024 plus 5 is 1029. So that is your using 11 bit you represented your biased exponent, and then remaining is your this fraction or mantissa. As we know that one dot we don't represent, so we start representing 11101111101000000, then 100, and actually I have represented all these numbers, and finally these all numbers. But if you go up to say 17 digit after that, if you put all zeros, there is no problem with that. Are you understanding?
Yes, 11 bit for the best.
Yes.
What did 11 bit for the
Best exponent.
biased exponent? Biased
Fine.
exponent is 11 bit. Yes, biased exponent is 11 bit. Yeah, this is biased exponent 11 bit, and this is your mantissa fraction. That's okay. So this is your mantissa fraction. You can represent it like this. That's a better one. I have used total 52 bits whole for representing that number. Actually 64 boxes. Making the boxes is difficult. That's why I have represented it like this. Any question, anyone? Boys, are you there?
Yes, everything is clear.
That's clear.
Okay, now we'll see that how to convert a single precision floating point number which is represented in computer memory, which has a sign bit, which has exponent, 8-bit exponent, and which has a mantissa. How can we convert it to the original decimal fractional number? Are you understanding the question? Are you understanding the question?
Yes.
So this is a representation is given to you. What you have to do, you have to go back to the original decimal fractional number. Are you understanding? So you can see that your sign bit is 1. That means your number will be negative number. It's not a positive number. So number is negative. And then you can see your exponent, 8-bit exponent. This is 1, this is 2, this is 4, 8, 16, 32, 64, 128 plus 3 is 131. That is our biased exponent, but that's not our original exponent. 131 is our biased exponent, and then our actual exponent will be, in order to get back your actual exponent, what you need to do? Anyone? From the biased exponent, if you want to get back your original exponent, what you have
Minus
to do?
127, I believe.
Yes, that is exactly what you have to do. So from your biased exponent 131, you have to subtract 127. So your original exponent is 4. So now what is our mantissa or fraction? You can see that this is our mantissa 0, 0, 0, then 1, 1, 1, 1, 1, then all zeros. So that's our mantissa or fraction. So in mantissa or fraction part, you can see first 3 is 0, so to the power minus 1 is 0, to the power minus 2 is 0, to the power minus 3 is 0, but to the power minus 4 is there, to the power minus 5 is there, to the power minus 6 is there, to the power minus 7 is there, to the power minus 8 is there. So if we take to the power minus 4, to the power minus 5, to the power minus 6, to the power minus 7, to the power minus 8, we'll get, after adding all of them, we'll get this one. Are you understanding how we are getting that?
Yes.
To the power minus 4, who can tell me what is the value of to the power minus 4? To the power minus 4 means 1 by 16, is not it? So 1,
It's 0.0625.
so 1 divided by 16 is 0.0625. So to the power minus 4 is 0.0625, then plus to the power minus 5. What is to the power minus 5? Who can tell me? 1 to the power minus 5 means 1 by to the power 5, which is 1 by 32. So 1 divided by 32, which is sorry, which is 0.03125. So if you take 0. So that's your 0.03215 plus to the power minus 6. To the power minus 6 means 1 by to the power plus 6. 1 by to the power plus 6 means 1 divided by 64. 1 divided by 64 is this value. So if you take that value, then you have to take to the power minus 7. To the power minus 7 means 1 by 128, 1 divided by 128, which is 0.078125. So we'll put that one plus to the power minus 8. To the power minus 8 means 1 by to the power 8, which is 1 by 26, 256, 1 divided by 256, which is this value. And if you add them all together, you will get the final value is this 0.12109,375. That's your mantissa, value of mantissa. But with this value, there is one dot, is not it? So there is one dot. So in order to calculate our value, what you have to do, we have to minus 1 to the power 1, which is a negative value. And here you can see that your value will be 1 plus this one, which is so better to use one dot like that one 1.1210937 So this is our fraction. So 1.12109375 into to the power 4, because our exponent is 4. Now you calculate minus and minus minus 1 into 1.12109375 multiplied by to the power 4 is 16. If you multiply all of them, then you will get what you will get. Let's see. This is 1.12109375 multiplied by 16. Why 16? Because this is to the power 4 is 16. So finally we are getting minus 17.9375. That's the representation of the number that is given here. So any question up to this? This is our mantissa part. You have seen the mantissa is 0.1210937, but mantissa along with one dot, it is basically 1.1210937 should be multiplied to the power 4, because our exponent is 4. So to the power 4 is 16. So if you multiply with everything, it is 17.9375. That's the decimal fraction of this number. So you have seen that how we can represent any decimal number using single precision floating point number, or any decimal number with double precision floating point number, where you use 64 bits for representing a decimal number. And here you can see that how we can get back our original decimal value when a fractional value is given, or when a memory representation of a single precision value is given. From there, how can we get back or go back to our original decimal value? Any question, confusion?
Clear.
Okay, the videos are already also there. Videos will be also there, inshallah. So if you don't understand this one, you can you can check it again and able to understand what is going on. Okay, now the last question of this one, but I want to take 2 minutes break. Can I have a 2 minutes break?
Yes, Doctor, take your time.
Yes.
Yes, doctor.
Okay,
You can.
okay. Okay, can you hear me?
Yes, doctor, we can.
Yes.
Okay, so we are going to do the last question of this class assignment number 7, how to do the floating point addition. And you can see that there are two floating point number we have here. One is 125.7x0, another one is minus 64.658. So one is positive number, another is negative number, but we can perform the addition operation. But this one will be normal binary representation. We'll do the binary representation of this one in binary scientific notation. But this one, since it's a negative number, first we will represent it normal binary. That is, means we'll represent it as a plus 64.658. Once we represent it as a plus 64.658, then we'll convert it to minus number. So once we convert it to minus number, then we'll perform the addition. So let's first convert them to binary. Then we'll do step by step. So convert both the operand into binary fraction. In order to convert both the operand to binary fraction, you can see that what we are doing, 125, this is a whole number, we can divide it by 2. 62 is the quotient, carry is 1. This is another way of converting any decimal number to binary. If you are confused, please try to understand. This is your positional value 1. You see that 125 being represented here, 125 being represented here. 1, 2, 4, 8, 16, 32, 64. So this is 64 plus 32 is 96, plus 12, 16 is 112, plus 8 is 120, plus 5 is 125. But you can get it using positional value like this, or you can get it 125 divided by 2. 62 is the quotient, carry is 1. Then 62 divided by 2, quotient is 31, carry is 0. These are your binary digit. And 31 divided by 2, 15 is your quotient, carry is 1. And 15 divided by 2, 7 is your quotient, carry is 1. So in this way, you can also convert, but when you convert, it will be from from bottom to top. So the first digit is 1, then 1, 1, 1, 1, 0, 1. This is the least significant bit. This is the most significant bit. So here you can remove that 0. So this is your most significant bit 1, which is represented here, and this one is your least significant bit, which is this one. And then we have a fractional part 780, and you can see that 0.78 multiplied by 2, 1.56, and 0.56 multiplied by 2, 1.12, 0.12 multiplied by 2, 0.24, 0.24 multiplied by 2, 0.98, 0.98 multiplied by 2, 0.96. This is 11100. We can go one more time. You will get. If we go one more time, I think we'll get 0.96 multiplied by, yes, any question? One point, who can tell me? So 0.96 multiplied by 2 is 1.92. So 1.92, we take 1. So this is 1100001. Yes, anyone? What you wanted to say? Nothing? Okay. So, but actually this is 5 digit. After this one, if you want to go, you can also go one more digit. This is 6 digit. So we should also make this one also 6 digit. So this is basically for representing 64 plus 64. So you can see that 64 is representing 1, 2, 4, 8, 16, 32, 64. So this is our 64. We can remove that one. So 1, 2, 4, 8, 16, 32, 64. So we have just taken 64. And then this is 658. 658 multiplied by 2, 1.316. 316 multiplied by 2, 0.632, like this. But since we have taken 6 digit here, we can also take 6 digit here. 0.056 multiplied by 2, that will give us again 0. Something. So our basically bits are 0 here. So our two number, let's see how what is our two numbers. 1.25780 is basically represented by this 1111101, that is 125, then this is 1100001. This is 64.658, so this is 100 dot 1010101010. Finally we got the result. What you have to do, you have to shift your binary point to the left so that you can get it in scientific notation, binary scientific notation. So 1, 2, 3, 4, 5, 6. So we shifted to the left 6 bits. So it says to the power 6. And we have shifted also this one to the left 6 bits. So this is also to the power 6. Since our exponent are same, we don't need to do any adjustment. As I told you today's class or last class for other section, that when you want to add two fractional number, their exponent should be same. So in the case when their exponents are not same, so you have to work with the lesser exponent and make some changes in your mantissa or fraction so that both the exponent is same. So in this case, particular case, this is, we are lucky that both the exponent is already same, so we don't need to do any changes in the fractional part or mantissa. But our this part 1, 64.658, this is a representation of plus 64.658, but we need to make a representation of minus 64.658. So what we have to do, we have to take this one and we have to convert their we need to flip it, add 1 to it, and then we'll get the corresponding minus 64.658. So convert the second operand into its 2's complement so that we can get minus 64.658, but this is our actually plus 64.658. So what we are going to do, we are going to write first what is our 64.658 plus 1.00000, how many zeros? 6 zeros are there. Then 101010. This is our 64.658, but this is a plus number. In order to get the minus of 8, so what you have to do, each bit should be flipped. So 1 becomes 0, 0 become 1, 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 1 becomes 0, 0 become 1, 1 becomes 0, 0 become 1, 1 becomes 0, 0 become 1. So we flipped each of the bit, then we add 1. So 1 plus 1 is 0, carry is 1, that 1 and 0 is 1. Then it will go, everything will go as it is. So you can see 1 will come down, 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 and this. So this is your representation for minus 64.658. And in fact, if you convert it, I have converted it, it will equal to 0.1111010101 to the power 6 is equivalent to minus 64.658. 658. So this is a correct representation. There is no confusion, but both now in the same scientific notation. So this is one mantissa, this is another mantissa. Exponent is same, so we just need to add the mantissa. So what we need to do, we need to add both the mantissa. If we add both the mantissa, you can see that how to add both the mantissa. This is the first mantissa 1.111101110001. So 1.110001110001. So we have taken the first mantissa. This is 125.780, and this one is your second mantissa, which is minus 64.658. So 0.1 how many ones? I think 6 1, then 0 1 0 1 1 0. So 6 1 0 1 0 1 1 0. So this is your complete mantissa. This is 125.780. This is minus 64.658. So we are adding the mantissa. 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, carry is 1, that 1 and carry 1 will give you 0, carry is 1, 1 plus 1 is 3, which is 1 1. So you put 1, carry is 1, 1 plus 1 is 0, carry is 1, 1 plus 1 is 1 1. So we put 1 here, carry is 1, then again 1 1 1 is 1, carry is 1, 1 1 1 is 1, carry is 1, 1 1 1 is 1, carry is 1. So that 1 and the carry 1 will become 0, and you have one extra 1. So this extra 1, as I told you, whenever you have a 10 bit number, if you get the result 11 bit, so you just have to discard that one. So this is not your result, so this just discard that one. This is your result of the addition. So this is 0.11110100001111 into to the power 6. But as we know that in our scientific notation, we cannot have, we can just remove this plus 1, this 1, and this is our result into to the power 6, but we need to normalize it. And if we remove, shift the binary point to the right, because to the power 6 we want to convert it to normal binary point. So or you can keep it as 1.110100001111. So if you answer the result in this way, or if you answer the result equal to, this one will be discarded. We are not interested about that one. But before the binary point, there is a 0 that we don't expect. So what you have to do, you need to shift your binary point to the right 1 bit. And if you shift to the right 1 bit, so it will be 1.111 010001111 into to the power plus 5. It will be to the power plus 5. So that is your actual representation of your result. So if you want to represent this one, you can do that. Or if you want to get rid of scientific notation, you just want to answer, you can answer like that. And finally, that's our rounding the sum. Basically, the result is this. If you convert this one to the corresponding decimal number, that's the result. And if you subtract these two numbers, if you subtract these two numbers, you will get the result close to it. You may not get exact result, but close to it. Any question?
In step number 1, Doctor, I can convert 125 and 64 by the calculator, right? I don't have to explain it here.
You can directly write this one like this one like this. Are you understand?
Yes.
Okay, but this one you need to show.
Yes, of course.
Any other question?
No questions, Doctor.
Okay, so we have finished our class assignment 7. Now we'll go back to class assignment 5, the last question of class assignment 5. So this is our class assignment 5. The first two questions we already solved. So you can also check the values. You can also check these values. You can write it there. And these are also the values that we did it in the last class. You can write that one here as well. This is not the right file. Yeah, this is the right file actually. So you already got the result of first two question. So I don't want to explain those two questions again. I already explained that one in the last makeup class, so you can take it from there. Just write it in the class assignment file, the due class assignment file. And now today we'll explain the third question, question number 3. Now this question number 3 is basically the last part of the addressing mode. As you know, the last part of the addressing mode, if you want, I can open the addressing mode chapter as well. Uh, uh, so you can see that last addressing mode was I hate this Windows operating system for nothing. So this is displacement addressing mode. You can see that displacement addressing mode, we have two mainly two types that we talk about. One is base register addressing and another is indexing, or and another one is base register addressing. In case of base register addressing, if you see that in case of base register addressing, what will happen? Uh, the reference register contains a main memory address, so there will be one register that will contain a main memory address, and the address will contains the displacement. That means instruction itself will contain your offset displacement, the problem that we solve in our array problem. You have seen that there is one register that contain your main memory address, which is the starting address of your array, and the we provide the displacement, that is our offset. So we add them together so that we get the effective address. That is the exact idea of what we are going to do here. You can see that assume that a hypothetical processor use the following instruction format. The instruction format is 24-bit for base register addressing mode, where the second source operand is stored in the memory. So in this instruction, you can see that 8 bits are used for the opcode. There is a one destination register, that means result will be stored in the register, and which register, that is specified using 4 bits. There is a one source register. So the source register basically contain your first source operand, and that is stored in which register, that is given here, and second source memory address register. So the second source, what is your operand, that address is given in a register. From that register you have to go to the memory location, and from that memory location you have to go to the displacement value so that you can get the effective address. So what we are saying that for base register addressing mode, where the second source operand is stored in the memory. So try to understand the instruction format. First 8-bit is for the opcode. So which operation you want to perform, opcode will tell that. Destination register 4 bits will tell that where the result of this instruction will be stored. In the destination register 4 bits will basically tell which of these 16 register you can store your result. The first source register, that means first operand, where is your first data, first source operand, that is stored in one of the 16 registers. So that will be specified here using 4 bits. But second source operand is not inside the register, rather it is inside the memory, but the memory address is not given here. Rather it is given here the address of the register. That means it is telling the register value that is containing the address. So register is containing the base address of your second source operand. Second source operand is stored in the memory, but we are not giving in the instruction itself, we are not giving the address of the instruction. Rather, the address of the instruction is given in one of the register. We are specifying that register number. Here, displacement basically given in the instruction itself, and displacement will tell you from the base register how far you need to go. So let's see, this is your register, 16 registers are there, and that's why you can see that every registers are, we have used 4 bits. So using 4 bits, actually you can represent, you can refer any one of the 16 register. That's why every register you can see 4 bits are there. Now, this is our main memory. You can see this is the address of your main memory. These are the content of the main memory. So with this register, with this memory, let's execute one of the machine instruction. The machine instruction that is given, that is also 24-bit as per our hypothetical processor can, it has the instruction format of 24-bit. So I have given a instruction for 24 bits. So first is the opcode. This opcode definitely can represent any operation that you processor can perform. It can be add operation, it can be multiplication operation, it can be subtraction operation, it can be any other operation. So this first 8-bit is your opcode, and then this 4-bit is basically telling you where the result will be stored, because this 4-bit is your destination register. So from these 4 bits, can you tell me what is the register number where our result will be stored? Can anyone tell me?
Isn't this the destination register?
This is a destination register. Can you tell me which destination register, which register will be used as a destination register as per this instruction? So first 8 bits, you can see the first 8-bit is your opcode. Your first 8-bit is your opcode. This is your destination register number. Which destination register? Which register is your destination register? Can anyone tell me? What is the destination register? Tell me, tell me.
R14 maybe.
Number?
14.
Are you sure? Or guessing?
Guessing. R14.
Why guessing?
R13, no?
R13. Why R13? What is the number given here? What is the number
R14,
given?
14.
R14, yes.
This is 1, this is 2, this is 4, this is 8, is not it? 8 plus 4 is 12, 12 plus 2 is 14. So that is exactly what we are saying, that destination register number will be given by 4 bits. So these 4 bits is representing number 14. So your register is 14, which is containing your destination register. So result of this operand will be stored here. Are you understanding? Will be here. So this 001 will be removed, and that will contain your final result. Are you understanding? Are you understanding?
Yes, clear.
So the first question, what is the current content of the destination register? Tell me, what is the current content of the destination register?
001. 000.
Because our destination register is 1110, which is number 14. So that's the register number 14, R14. So our current content of the destination register is, anyone trying to ask any question? Anyone trying to ask any question?
No.
No. What is the content of the first source register? From where you get the first source register number? because as per the instruction format, first 8 bit is the opcode, then second 4 bits is the destination register, first source register, that means your first operand is stored in a register. And which register? Can you tell me? Which register?
12.
12. This is your first source register, is not it? So this one is first source register, the register number is 12. So register number 12 is containing the value 008A. So what is the content of the first source register? The content of the first source register is 008A. So this is the first source register content. And then what is the address of the second source memory location? So second source memory location is given in the instruction. Memory location is given in the instruction.
Yes.
In the instruction.
No,
Memory location. Second source memory location. That means your second operand. Where is your second operand? It is in the main memory. We have already specified that one. The second source operand. You see that where the second source operand is stored in memory. So second source operand is not stored in the register, but in the instruction, are we giving the address of the memory location, or I am giving the number of the register?
register, no.
Number of the register. So this 1001, this register, what it is containing?
5032.
The memory location.
So 1001, what is the register number?
9.
9.
It's number 9.
9. So if you go to the register number 9, which is it containing any value, or is it containing an address of a memory location?
Address.
Containing the address.
So 5032, this is the address of the memory location, is not it? So try to understand, you register in your instruction, your second source operand is stored in a memory location, but in the instruction we are not specifying the address of the memory location, because address of memory location requires 16 bits, but we don't have 16 bits in our instruction itself. So what we are doing, we are storing the address in a register, and we are specifying the register number in our instruction itself. So in our instruction, we have given the register number 9, which is containing the address of the memory location that is containing your second source operand. So what is the address of the second source memory location? Address of the second source memory location is 5032. Is it 5032?
Yes, 5032.
Why? Is it the effective address 5032?
Yes.
No, it is not the effective address, because second source memory location is given in register number 9, but after that, that is the starting address. That is the starting address. That's your base register value, but you need the displacement. What is the displacement given here?
4.
4. So your 4032 plus 4, what will be the value? 5032 plus 4. 50.
Why we are adding the displacement?
That is the addressing mode. That is the addressing mode is telling that your effective address is calculated based on the source, so the source memory address register value, which is your base address register value, plus the displacement, that is your effective address, while your actual value is there. In the array accessing, you have seen that in case of array accessing, in order to access the 8th element of the array or 7th element of the array, we need the base address. We start with the base address. With that, we add the displacement. We get the 8th element or 9th element. So in order to get a particular value, you have to first know the base address. Once you know the base address, you have to add the displacement to it, so that you can get the effective address of the your source operand. Your source operand is not stored here. This is the starting address of your array. It can be array, it can be anything, but this is a block of memory where the starting address is 5032, but you have to add the displacement to it. So displacement is 4 here given, displacement 4 is given. So what you have to do, 5032 plus 4, which is 5036, is your actual address, effective address. If the opcode of the above machine language instruction refers to multiply instruction, what is the new content of the destination register? Will show you result in hexadecimal. So what is your value of 5036? What is your second source operand? What is your second source operand? Who can tell me?
0083.
0083 is your second source operand, and your first source operand is 008A. If you multiply them together, let's go to programmer, hexadecimal 008A. So 8A multiplied A3. A3 is result is 57DE. So your final result is 57DE. 57DE. Are you understanding what I'm saying? I'm saying that if the opcode of the above machine language instruction refers to multiply instruction, then what is the new content of the destination register? Show you result in hexadecimal. Since your first source operand is 008A, second source operand is stored in 5036 memory location, which is containing 0083. So you have to multiply them, and the result will be stored in your destination register. And this is the result after multiplying. Are you understanding?
Yes.
Yes.
So you need to understand that when it is a base register addressing, the starting address of the memory location where your one of the operand is stored, you can get it from the register. Register will contain the address of the memory location, that is the starting address. From there you have to get the displacement so that you can get the effective address. Are you understanding?
Yes.
Good. Hopefully you understood. Now, one more thing I need to explain you. In case of indexing, both are same. Remember, displacement addressing. One is base register addressing, another is indexing. Both are same. Just a slight difference between that. In case of indexing, your source operand is not going to be stored in a register. Rather, the main memory address will be given in your address field. The address of the main memory will be given in the address field, but displacement will be stored in one of the registers. Are you understanding? In case of indexing, the difference between base register addressing and indexing is that in base register addressing, the address of the memory location of the second source operand is stored in one of the registers. So in the instruction itself, you don't contain the address of the memory location, rather you contain the register number. You go to that register number, you get the base address of your memory location, and with that base address you just add the displacement which is given in the instruction itself, and then you get the effective address. But in case of indexing, your instruction itself will contain the total address of your second or first source operand. Any one of the operand, direct memory address will be given in the instruction itself, but your displacement will not be given in the instruction itself. Rather, displacement will be given in the register, where register number will be given in the instruction. So from the instruction, you have to get the register number and go to the register number, get the displacement. Displacement will be added with the memory location address that is given in the instruction itself. That is the way how you will calculate the effective address in case of indexing.
Doctor,
Is it clear to you?
yes, this slides is are in the blackboard.
Yes. Index
can't find it.
addressing. Huh?
Oh, addressing.
Can't addressing. This is addressing. Displacement addressing has two parts. One is base phased addressing, and there is indexing addressing. Okay. So that is the end of our class. I hope you understood the things. Do practice at home so that you can do well in the quiz and improve your grades. Okay.
Okay, thank you.
Okay.
Thank you, inshallah.